Hi. Okay. I'll talk today about interactive algorithms in pool and stream settings. So first, let's say what I mean by interactive algorithms. I will talk about a very general sense of interactive algorithms. So just any algorithm that iteratively selects elements from some data source, observes responses for the elements it selects, and until it finishes. So this is a very general notion. It includes a lot of different applications. A very important one is, of course, active learning, which is a type of an interactive algorithm, but also a lot of other applications, just to name a few, interactive sense replacement, interactive promotion in social networks. We might want to choose user to get a promotion to, then observe the response, then decide on the next user, etc., and many others. For this talk, I will again consider a very abstract notion. So we have an algorithm and we have a data source. The data source has elements. I will note them x1, x2, etc. And it has each element has a response, which is in the beginning hidden for the algorithm. But then the algorithm iteratively selects elements from the data source, and every element it selects, it gets a response. So in active learning, the element could be an example, and the response could be a label. In other applications, it could be anything else. So maybe X is a sensor, and Y is a measurement of what the sensor has observed, etc. And again, keeping with the generality, the reward of this algorithm for me is just some function of the output. So I will not focus on the specific function. I will just assume that given the output, which is the x's and the y's that were selected, I have a reward. Now, what I will focus on in this talk is the two very different but both very important types of interactions with the data source, which is the pool interaction and the stream interaction with the data source. So what do we mean by that? In the pool setting, we assume that the data source has some finite set of elements. The elements are known to the algorithm in the beginning, and then the algorithm can interactively select any of the elements in any order. In the stream setting, we assume that the available elements are observed one by one. So, for instance, you can think about maybe a website where users log in, buy something, then go out. So we see a user, they log in, they leave, and only when we observe them, we are allowed to select them. We cannot go back and select them later, only when we see them. So this is the stream setting. Both settings have been really well studied for different applications. A lot of work in active learning, both in the stream setting and in the pool setting, and some works that apply to both. Works in interactive learning as well, interactive algorithms as well, both in the pool setting and the stream setting. In some regimes, for instance, in active learning, we actually have results that show that the pool and stream setting, they seem near equivalent in some settings. But what I want to ask here today is, what is the general relationship between these two settings in a very general sense for general interactive algorithms? So to start to think about it, let's be a little bit more formal. So we'll assume some distribution D over x's and y's. X's are the elements and y's are the responses. And as I said before, the responses are going to be hidden at the beginning. The data source that the pool has is some IID draw of pairs, M pairs from the distribution, and it can observe all of the elements. The data source of the stream is essentially, it could be basically an unbounded stream of elements, and every time it sees an element, it can decide whether it selects it or not. We will consider a pool and a stream algorithm equivalent if their output distribution is exactly the same. So this is why I said before that I don't consider the specific reward function, because I'm going to look for algorithms that are totally equivalent in their output, which means that any function that I apply to one will be applied just the same to the other. And what I'm interested here in this work is whether we can emulate a black box pool algorithm using an algorithm that works in a stream setting. So why do I care about that? Because if I can do that, this means that I can take any pool algorithm and use it in a stream setting. And if the cost, which I will consider in a moment, is small, this means that the difference between the pool setting and the stream setting is not too large. So what do I mean by cost? So when I say cost, I mean information costs in this talk. So I'm interested in the one cost, which is very important, is the expected length of the stream that is needed to emulate a pool of size m. So the pool can get away with m examples and see some distribution of outputs. What is the length of the stream that is needed to emulate that? Another possible cost is if I allow the stream algorithm to select more elements than the budget, which is q, how many more does it need to select to get the right output distribution? And my goal here is to get distribution-free and algorithm-free guarantees. So I want to get guarantees that are as general as possible. We studied two cases in this work. One is the general case, so just a general pool algorithm, and what can we do about that? And the other is a more specific case, which is very useful in many applications, which is utility-based pool algorithms, by which I mean any algorithm that in each round selects the element based on some scoring function, which it just wants to maximize. So any such algorithm, and many algorithms in the literature match this property, is a utility-based pool algorithm, and I can ask what is the possibility of emulating such an algorithm. Our main results, I will show some of them later, but just to give the general idea. So our main results include emulation algorithms for both settings, with upper bounds matching lower bounds, and for both cases. And we also show that in the utility-based setting, we actually can derive also a specific case for binary active learning, where even for binary active learning, there could exist significant gaps between the pool and stream sizes. So let's start with a general setting. And here's, okay, so I will not go into all the details, but we have an algorithm for the general setting. This algorithm basically is able to emulate exactly the distribution, the output distribution of any pool algorithm, which is given as a black box. So the algorithm uses many simulations of the run of the pool algorithm, and based on the simulations, it decides which elements to take. And what we can show is that this algorithm, first of all, is exactly equivalent to the pool algorithm. We can also show a uniform upper bound on the stream length that this algorithm uses in expectation, which is going to be essentially m to the power of q, more or less. And we can also show that this is actually necessary. So any stream algorithm with the same properties, which emulates any pool algorithm, will need actually a number of a stream length which is exponential in q over 2. So this is actually quite close to the best that you can get for this general problem. And the proof ID for the lower bound is that we need a pool algorithm that constructs, that is very global. It's a pool algorithm that looks at the entire pool when deciding which is the next x to get. So I will just mention that, because of time, that for utility-based setting, we can get a much better result by using the solution to the famous secretary problem, which allows us to actually select, to at least attempt to select the best element in a stream quite easily with a good probability of success. And we have an algorithm for this case too. And for this algorithm, we have much better guarantees. So the stream length, the expected stream length is O of q times m, so linear in the number of queries. And this is also quite tight. You can't do much better than that according to our lower bound. And also from this, we get a similar result for binary active learning. So there are binary active learning problems where you can have about this gap as well. To finish, my take-home message is, first, that there is an unavoidable gap between the pool setting and the stream settings in the general case. It is smaller for utility-based algorithm, but it does exist. And it exists even in binary active learning regimes. And here there are a lot of open questions. One of them is, what is the trade-off between the stream length and the number of elements that you're allowed to get? Because there is a trade-off here. And other is specifically for active learning, what happens under different interesting regimes for active learning. And there are other open questions as well. Thanks.